All right, we're continuing on to, it's been a while, I know, since I made another part of the Intro to Quantum Computing series, but I figured I should get this out before I do the QOSF What Not to Do Part 3 video, which is the, custom circuit simulator. So yeah, this is just a theory video, I guess. And we're talking about multi-qubit gates. So we already talked about single qubit gates, eigenvectors, eigenvalues, Hadamard, etc. So we know that if we have two circuits, or two qubits, sorry, in the zero state, right? Hold on, just a sec. Okay, I don't know if you could hear that, but my neighbors were being loud. So anyway, getting back to it, right? Just some notation. We have our quantum bits here, and they're often represented in a circuit reading left to right, as you know, language, English does. And we can draw our little gates on here however we want. And so that's the usual visual notation of circuits. But when we're talking about specific wave functions, right, like at this point, we'll draw these, you'll see tensor products a lot, or Kronecker products. You'll see that a lot. And so what that means is basically this state right here is converted into this. And so all of these are almost always, or in this context, equivalent, right? You can draw them like this, or you'll often see it like this. And in the context of multi-qubits, you'll see it sometimes like this, because then you'll see higher numbers. So rather than writing out, 52 or something like that, right? If you don't want to have all of these long bit strings, you can write out the whole numbers. But that's probably not very helpful. So we know this notation now, right? We can see, okay, for multi-qubits, we're just sticking to 2 for now. We got this simple notation. There's a lot of multi-qubit operations, but first we're just going to talk about the important result. Actually, first we'll talk about the CNOT gate. I'm sorry. So if we have 2 qubits, we have the CNOT gate or controlled X gate, which is drawn like this. And the matrix form, I should probably make sure that I'm not, lying to you right now. Yep, I was right. It is 1 0 0 0 0 1 0 0 1 1 0 0 0 0 0 0. Okay, that's the CNOT gate. And so what does this do? Well, it's sort of like classical controlled NOT, where it's like where the control is the little dot and the NOT is this part. So if this is a 1, then this becomes flipped. So you can see it as transforming 0 0. It does nothing if this first digit is not 1. So 0 1 goes to 0 1. However, if this first digit is 1, then it operates as control, and so that functions as true, and so it creates a it has an effect. And so that's not particularly exciting, right? Except there's 2 results that are, I mean, this is a super important gate, but there's 2 things I want to talk about first. And one of them is okay, so if we have a classical state, right? If we have a classical bit right here, and by the way, if you're following, this part's pretty much very strongly inspired / taken from Mike and Nike, Quantum Computing and Quantum Information. So you're welcome to look at that. So if we have some classical bit, right, and we want it to go into this magic little box, and we want it to come out, and we want a new bit, we want to duplicate it, right, basically, we can simply do 0, what's the notation for or? Oh yeah, or. Okay, there's so many things I used to double lines up. I'm realizing now that's like a Kale divergence and stuff. You all see that. We can do that. That's a valid symbol. And X. So think about it. This is 0 or 1. And then whatever it is, that or 0 is the same thing. And so we can duplicate this, right? This is easy. Just, I mean, you could probably write out, if I remember back to Comporg, right? You could probably write out the exact circuit logic that would do this. It's very simple. Actually, I don't know why I say I have to remember. Is this the OR gate? Okay, one of these is the OR gate. I don't remember which one, but a quantum circuit, right? That's not so easy. If we have our input state, which is just a qubit in an unknown position, and we want to duplicate it, right? So we want our circuit. Over here, we want that state, and then we have 0, and we want that state. And we can do anything in here. Can we get, can we clone this state? Can we duplicate any unknown quantum state? And the answer, in short, is no. This is impossible to do. And you might be thinking, is it really, though? And it is, in fact, and it's pretty trivial. No cloning theorem is what it's called. It's pretty trivial to see. And so we know that the state, for example, this wave function, right, input, we can see that, okay, this is some, state. It's some superposition of states, right? That's what it definitionally, every qubit is that, so it has to be that. And so we can see, okay, well, let's get the tensor product. So we know that this is equal to because we can just distribute this. It follows the same simple rules as multiplication. Tensor product is kind of like that, and the rules it applies. So we can do that, distribute it over FOIL or whatever it's called. And so we get the circuit state, right? So at the beginning, we have, well, mouse is acting up. We have, right? So this is our goal. Do goal here. This is our circuit. Okay, so right here, this is our state. Okay, and at the end, right? This is our goal. What we want to happen is we want it to be a superposition where we have alpha. Sorry, I just have to write this out. So if we're copying this over, right, we can see the. I might need more room down here. Yeah. So right. So our desired state is this. This is the goal. I'll write it again down here. And so we can once again do FOIL. So we can do alpha squared 0, 0 plus beta 0, 1. I'll continue on this next line, plus beta alpha 1, 0 plus beta squared 1, 1. And that would be the state of our system. And we'd have 2 qubits. And so we could separate this out, obviously, as a, this could be represented as alpha 0 plus beta 1. And do that twice, alpha 0 plus beta 1. That's pretty exciting, right? That's what we want. That's cloning it. So how would we do that? Well, let us suppose that the CNOT gate, right? That seems pretty useful. We could go back and we could see, well, why don't we just use the CNOT gate? Well, you can see in Mike and Ike, they show what happens if you try to do the CNOT gate, which I'm not going to deal with right now. But the key takeaway is that if we had a system, right? So we can see there that if we take the initial input, which we'll write here, and suppose we had a way to convert it to this goal. So we have some operator, right? U. This big circuit is U. Suppose that exists. I'll just do U clone. I'll just do UC. Where it takes a state here, some sort of qubit, and it maps it to a to copying this into this. So we have an operator that does what does UC do? UC takes this state here and maps it into this state here. Well, now let's try that just with this expansion right here, right? So we know that what this wave function equals. Actually, I'm not going to do parentheses. So if we just expand it out, we can see alpha 0, then we have 0, and then we have plus, we have beta, and then we have 1, and we have 0. And so if we apply this U thing, right, onto this, we would get alpha squared 0, 0, beta squared 1, 1. Because remember, we're just saying, okay, we're copying this into this, right? That's what the operator does. It copies a quantum state into this state. But that's, you might be saying, hey, wait a minute. This state is equal to that, right? But this does not equal that. So we have a contradiction here. And this is proof, right? Proof by contradiction is saying, hey, wait, this operator, when you do it on just a different form of the equation, results in two different things. And so it's impossible. There's also another way you can prove this using the inner product operation, but I'm not doing that. So that's an important result in quantum information theory. And that comes up a lot, even in quantum machine learning, everything. That's an important note. And so the next thing on the docket is the Bell state. So this is oopsies, that's not what I wanted. This is basically, right, also known as, I should do EPR. So Einstein, someone wrote a paper back in like 36 where they're like, hey, wait a minute, quantum mechanics sucks because it's not complete. I'm obviously paraphrasing their interpretation, but it's a famous paper in which they say, hey, wait, this state, this can't exist. It violates, what we consider. And so turns out the state can exist, and so it's a little awkward for Einstein. I mean, he's dead, I guess, but it's the physicist Bell proved that this exists in his experiment, a famous experiment that he did. But basically what it is, not particularly exciting based off of first look, but we have two qubits, this 2-qubit state. It's an equiprobable state. And you think, okay, hey, wait a minute. Remember that entangled qubits have nothing to do with physical distance. I mean, it's easier to keep things entangled when they're close by, but that's not at all a physical constraint, theoretically. So we could say, okay, let's have Alice over here. Let's entangle this state. Now, Alice and Bob, that's why I'm using those names, because they're standard in cryptography. Alice takes qubit 1 over here, and Bob takes qubit 2 over here. And now the state goes to each of them. And if Alice measures her state, it collapses, right? Remember, you only get one measurement of the wave function. It collapses. And so we can see that if she measures this, if she measures a 1, Bob will also measure a 1. And so note that this doesn't allow for faster than light traveling of information, right? Because Bob doesn't know what Alice measured, right? She has to tell him, oh, I measured 1, now you can measure or something like that. But it is an interesting phenomenon. And so how do we get there? Well, we start off with our state, our pretty little state 0, 0. We do a Hadamard gate and we do a controlled NOT gate. And that's it. That's all of it. Very simple, but you're probably wondering, well, that doesn't make sense. How do we get there? So remember, looking at the initial wave function, we do 0, 0. Now we do h of 0, 0, 0. That's probably bad. H of 0, 0. And this gives us, so now we have a superposition, right? 1 over square root of 2, 0, 0 plus 1, 0, because we put the superposition in on the first qubit, and also this is also where I'll talk about entanglement. Actually, I'll do that briefly. I should have done this before. The Bell state is the first thing where we're going to see the quantum phenomenon of entanglement, and we saw superposition previously. Now we just accept it. So entanglement, right? If we have this state, like I just drew down here, 0, 0, right? We can easily just separate this out, right? We can just do 0, 0. We can take them apart. We can pull them apart. We can do whatever we want, right? They're mathematically separable. But if we have some state here, right? That's you can't separate these qubits. And so more formally, what would this look like, right? So if we have our separable state, then we can write it, as a we want to represent this as two distinct, I can't undo it, oopsies, operations, right? We can, if we have, I'll just make that lowercase b, c 0 plus d 1, right? This is easy to do. This is, so we know a equals 1, c equals 1, b equals 0, d equals 0. And we know that this, that's what that corresponds to. But now let's expand this out, right? So we know it's a c 0, 0 plus a d 0, 1 plus b c 1, 0 plus b d 1, 1. Right, this is just this expanded. Now let's say, okay, that's what it means to be separable, right? We can look at each qubit individually and have a complete representation of the wave function. But if you're saying, okay, well, let's look at this, right? Let's express this. So we know two things. We know AC equals 1, and we know BD equals 1. We also know AD equals 0, and BC equals 0, which means that A or D, one of them has to be 0. But hey, wait a minute, if A or D is 0, then one of these has to be 0, which means that it wouldn't exist. So there's a mathematical impossibility here. And that means that these qubits cannot be mathematically separated. Their wave function is entangled. And that's what that means, is that it's basically not linearly separable. I mean, that's not very exciting by itself, but that's an important phenomenon, right? Like, hey, what does that intuitively mean? Or, it's hard to grasp the physical reality of it. Now, I'm not going to get into all of what that means right now, but that is something, to struggle with from a philosophical point of view as well. So that's, why this is so important. And so now we can get back into doing the math of it. So after this state, right? So we have this here. Now we have this. Now let's apply CNOT, right? So what does CNOT do? Well, it takes every 1 Now, remember when we were looking at just a simple ground 0 or 1 states, it just flipped it, right? But the same principle is true of any sort of complex state, and that's the beauty of it, is it's actually pretty simple to do. So if we do CNOT now, we can see that, okay, well, the CNOT operator, right? These operators, you can just look at the sums, right? So it's CNOT of this. So remember, the input is 0, so it has no effect. So this results in 1 over square root of 2. It's a really bad drawing. And so remember here, 0, 0. Let's go back to our little page, right? 0, 0 goes to 0, 0. Okay, now what do I do with this one? Let's go back to this page. I mean, I know, but so we have 1, 0. That goes to 1, 1. Okay, that's pretty nice. And that's our Bell state right there. That's the final wave function. And so that's an entangled state as well. And hey, that's pretty neat, right? And so that's the breakdown of how you get this entangled Bell state, and that's a really common thing. You'll see people talking about this state a lot. And so the last part, I'll make this quick, is it's called teleportation, quantum teleportation. So let's suppose Alice and Bob each share an entangled qubit. So we have Alice's qubit, Bob's qubit, and Alice has an extra one up here, right? So they go in and they form a Bell state, right? Now they walk away. So this is like a physical separator. Bob goes to Japan and Alice goes to London. I think that's, halfway around the world. Now what Alice does with her extra qubit, actually I'm just going to change this to be this is a wave function that has some information. So remember, this is alpha 0 plus beta 1. And she wants Bob to know this information. She wants to teleport this bad boy right across the world. So what she does is applies the CNOT gate, applies the Hadamard gate on this one. Remember, these are going through. And then she performs a quantum measurement of both of these. And because these are all, remember, you can have triplet entanglement as well. I just gave an example of 2 states, 2 qubits being entangled, but you can have 3 qubits entangled as well. This results in Bob having this wave function. There might need to be some modification, by the way. I'll get to that in a second. But so let's go through this. So the initial wave function, we have this representation, this 3 qubit representation. So I'm just going to drop all the probability from the front. I just don't want to deal with that. But notice that there is, however many terms there are, they're all equiprobable. But I'm just dropping that right off the bat. So we know we have this 0 term, and we have it times the Bell state plus 1, 1. And we have this beta term, and we have our Bell state, right? And this is what the wave function is right here, because we just created the Bell state last slide, so we know what this is. So this is what's going on right now. So now let's do the CNOT gate, right? To controlled by this qubit onto this one, this one, this one, this one. So if I rewrite this, if I expand this out really, we can see that this is pretty simple. So remember that 0 has no impact, so I'm just going to leave this completely as is. Right? There's nothing that the 0 does for a CNOT gate. And so we do plus beta, and now this time it does something, right? This changes, this flips the value of the first circuit. or the first qubit in this pair, because remember, when it's a 1, it flips it, right? So let's go back, and we can look, and we can see, okay, hey, 1, 0 goes to 1, 1. So we can put this here, and we do 1, 0. And we do this, and we do 0, 1, right? Because this caused these bits to flip. The latter two are this one and this one are the exact same because there's no CNOT gate there. So now we, this is this here. Now we're going to do the Hadamard gate. So what does the Hadamard gate do? Well, I mean, that's pretty pretty straightforward, right? It converts the 0 state. The Hadamard converts the 0 state into. Actually, let's take a quick detour. Maybe can I reorganize these? Yes, I can. Onto what the H gate does. I know we've discussed it before, but I just want to do a quick deviation. So H of 0 equals, and once again, I'm dropping the probabilities because, right? And so, and H of 1 equals 0 minus 1. So how do we collapse it, right? So if we do H of 0, and then we do H of that, right? We see that, okay, so we have 0 plus 1. Now we do H on each of these. So this becomes 0 plus 1. I guess I shouldn't actually drop the probabilities. This becomes 1/2 0 plus 1/2 1. And this one becomes 1/2 0 minus 1/2 1. Add them together, we get 0. Okay, so that's just a quick deviation, right, of how this works. So we can go back and we can say, okay, let's apply the H gate here and the H gate here. What do we get? We get, we get A. Excuse me. We get A times 0 plus 1, and then we have our 0 0. Oop, I don't know what happened there. 1 1, and then we have our plus beta parentheses 0, and then we have minus 1, and then we have our 1 0, then we have our plus 0 1. So now we can do some easy rearranging, right? If we just expand this out a little. So what do we need to do? We need to say, okay, let's just do this. So we just expand it out, and we can see that after the expansion, the result can be basically rewritten. Just, you know, you have this long nasty equation, but the good news is you can rewrite this in a somewhat easier way. Maybe I'll erase. Can I expand this at all? I don't think so. Here, I'll just erase the previous parts. So we can erase this, erase this, erase this, erase this. So we can keep our current state, right? And so this is the state. So we're going back up here. Notice that we're distributing the A's even if I don't do that explicitly. So let's group by these terms instead. And so we can see one thing that's readily apparent is rather than, oh, sorry, I did not mean to say group by those. Rather than saying, let's group by the shared qubits or the split qubits, right? Let's just look at the first two. And so let's find So this is, there's basically no parentheses here. It's all just added. So there's a 0, 0. I bet there's another one somewhere, and there's a 0, 0. So let's write that term. So we have alpha. So we have 0, 0. And notice that although this is in the same notation, this 0, 0, this is not equal to it. This is not the same thing, right? This 0, 0 refers to the first 2 qubits up here. And so its order is essential, right? Left to right is also the same as top down in these qubit systems. And so do not think this, like these are Alice's qubits, not Bob's and Alice's. So we can do this plus beta 1. Okay, so now let's get rid of that. So we can get rid of that term, get rid of that term. So now we can do plus, and then we can do 0, 1, alpha 0 plus beta 1. And remember, these ones with the alphas and betas in front is Bob's qubit, not Alice's. The first 2 are Alice's. This is the same equation. I'm just rewriting it. And so now let's get rid of them. So we have 0, 1. So that's a 0, 1 right there. That's a 0, 1 right there. And then we have plus 1, 0. So we have a 0 plus. Ooh, actually this time it's minus B1. So we have the 1, 0 right here, but this time the 1, 0 is negative, and it's the same with the 1, 1. So we do alpha 0 minus beta 1. That's that one, and that's that one. And so now we can see if Alice, so there's 4 possibilities, right, for the measurements Alice makes. But if Alice makes her measurements, she's going to get one of these states, right? Let's just suppose for simplicity, she measures the 0, 0 state. Bob, therefore, has Alice's original state. So Alice said, I have this information that Bob, remember, they never saw it. This is all isolated beforehand. That's never been seen before. I have this qubit in there, and I teleport it to wherever Bob is, right? And this is the exact information now in Bob's qubit. However, 2 things. One, you might think, hey, wait a minute, didn't she just clone it? You just made duplicate information. That's not the case, because no longer are, one, you had to measure it to get there, and so it destroyed the original qubit, and 2, you did all these operations, so the original qubit is no longer the same wave function. Hence, it's not cloning. Transferring is entirely possible, but cloning is not. In addition, you might be thinking, well, teleportation faster than light, hey, that's a great idea. But the problem is, Alice can measure any one of these, and in order for Bob to have the qubit, she needs to tell him if he needs to apply a Z gate here, right? Because it's entirely possible that, oh, I just realized I made a mistake too. I messed up. This is probably very confusing for those of you who caught it. I did not do the reading correctly. Yeah, so you can see here's the mistake. For example, 0, 1, A controls this 1 qubit, not 0. So that's my bad. I just miswrote it. And you can see there needs to be some sort of Z and X gate here if Alice is going to convey this information to Bob. But the probability amplitudes are still there. This A comma B is still in Bob's qubit. And I think just recently there was a new demonstration of like record distance for quantum teleportation, but you might have to look into that separately. And so that's pretty much the basics right there. That's pretty much everything needed before we get into the custom circuit simulator, which I'm pretty excited for. So that's entanglement, right? This phenomenon of entanglement, EPR, and multi-qubit operations.